Okay, good afternoon, everyone. So we're very happy to start with the first talk of the afternoon by our own Adrian, who's going to tell us about the homotopy theory of differentiable sheaves.
Right. Okay, so I'm going to pick up where Kalal was talking about this morning. I'm going to talk about configuration spaces. But my configuration space will be much simpler. There will be no graphs or anything like that. I'll just consider the following. So consider the configurations in Rn, and these are just subsets of Rn like this, such that these are always just finitely many, like this, cardinality smaller than infinity, and it's topologized in a certain way. So here's a picture of Rn, and here are a bunch of points. And so if you want to understand the topological space, you can map into it from R and see what happens. So a path in here is just these points will be wobbling around in a continuous way. But one thing that can happen is that a point is allowed to disappear off the edge of the world, and you can also import points from the edge of the world. So this is a connected space, right? Because you can always add and remove points to get all the different cardinalities. So does anyone know the homotopy type of this topological space? So you're not allowed to answer because you already know. Does anyone else know? So the homotopy type of the space is just given by Sn. This is just the n sphere. Good. That's the look I was hoping for. And so Sadak is showing me a really nice proof of this in a paper by Siegel, the configuration space of rational functions. Like from the 1970s or something.
The topology of rational.
Right, topology of the topology of the space of rational functions. Siegel does the following. He says, okay, so let's give this here a snap here name. Let's call it C. Siegel says, okay, so consider the following subspace. We can just consider those configurations in C such that the intersection of C. I got messed up here. I wanted to give this space here a name. C epsilon, and this sits inside of here. There we go. Such that K intersected with B epsilon 0, and this is the open epsilon ball, is smaller or equals to 1. Right, so the picture you should have in mind is that you have a little epsilon ball here in the middle, and then here you have at most 1 point. So maybe 1 or maybe 0 points. And then this space here will be equivalent to the following. This will be equivalent to just those configurations in C such that the cardinality of K is just smaller or equals to 1. And how do we see this? Well, if you have such a configuration with at most 1 point, you can just push everything outside of this epsilon ball. You can just push everything off the side of off the edge of the world, and then just left with at most 1 point to the side. And you can do this consistently. You're just like deforming the underlying ball on which your points live. But this here is nothing else than the 1 point compactification of Rm. So this here is just Sm. And then Siegel says, well, for epsilon prime greater than epsilon, we get, for varying epsilon, we get this system of spaces like this. And then he just writes very mysteriously, well, these spaces cover this configuration space, and therefore the configuration space itself has homotopy type Sn. All right. Well, he's Siegel, so I believe him, but but why is this true? And we'll see why this is true. And we'll see that the reason why this is hard to understand is because because of the following. So there's the following critique of the category of topological spaces. So I have 2 points. Point 1 is that geometric spaces can be hard to define. So by geometric spaces, I mean things like this configuration space. So this configuration space per se is not so hard to define, but we'll get similar spaces which are hard to define. And secondly, we have like this topological space is just like a bad model for homotopy types. So what I mean by this is take any property of the category or the model category of simplicial sets that you love, and if topological spaces doesn't have it, this is the sense in which this is a bad model. And so in this talk, I will suggest an alternative to topological spaces. And to introduce this alternative, I'll first introduce quickly a certain infinity category, and then we'll get back to ordinary categories again, but I'm doing it this way to tie in more nicely with the rest of the talk. So you can consider the infinity category of hi Thatcher, homotopy type value Sheaves on the site of smooth manifolds. So this infinity, it stands for smooth, not for infinity categories or anything like that. And then whenever you have an infinity category, inside of there you'll have located the subcategory of zero truncated objects. So the zero truncated objects in homotopy types are just sets. And then similarly, the zero truncated objects in this topos here are just going to be the set value Sheaves. And so I said that this here is supposed to be a good replacement for topological spaces. So we have theorem A.
I'm sorry, what does that say? What value Sheaves?
Oh, set. So this homotopy type. This is just S is the infinity category of homotopy types. Theorem A, originally due to Szynski. See, oh, that's not how you spell Szynski. This is how I spell it. Szynski. And I'll give a different proof from this talk. So this diff zero truncated is a model. For S, for homotopy types. And I want to be a bit vague about what I mean by model, but if you don't want to be vague, it just means that this, well, one way of making it not vague is to say that this has a model structure which models homotopy types. And so before I get to theorem B, let me address this first point here, which is that that it now becomes easy to define many interesting geometric spaces. So given so I'll consider the following example. So consider a manifold. Consider a smooth manifold X. Then you want to define a space psi d of X which is supposed to be the space of d-dimensional submanifolds, closed submanifolds of X. So for example, if D is equals to 1 and X is R2, then you have like one-dimensional submanifolds of R2, and you want to topologize in some way so that you can actually push these one manifolds off the side of the world. But you see that as you push this one manifold off the side of the world, you're changing the diffeomorphism type of these manifolds. So actually accounting for this is very hard topologically. It can be done. There's this paper called Monoids of Classifying Spaces of Manifolds by Glaciers and Random Williams, and this is like a 2-page definition, and then like another 2 pages of lemmas to show that this definition actually kind of does what you want it to do. But as a sheaf of manifolds, this is very easy to define. Right, so this is supposed to be a sheaf. So for all manifolds, we need to define some set like this. And well, when I explained this picture, I said we understand things by mapping into them. So by Ueneda, I can say this is the same thing as mapping in from M into psi dx. So I'll get to this perspective in a second. So this here is the following set. It's the commutative triangles like this. So these are commutative triangles of smooth maps where this is just like the trivial X bundle on M, and these have properties. This here is a closed embedding. Closed embedding. And this here is a submersion with d-dimensional fibers. So a d-submersion. So let's draw a picture. Let's say we have d equals to 1. Sorry, d equals to 0, sorry. And then, so for our original configuration space, we took M to be a path because these are nice. So we have M equals to R, and let's take also X equals to R so that we can actually draw something. So now let's draw this guy here. That's going to be like this. Oh, can you see all the way down here? Okay. So we have M and X. Okay, so now we have this part, and now we're supposed to have a submersion. We're supposed to have an embedding with 0-dimensional fibers. So this has to be a 1-dimensional guy. So it looks like this. And this here, according to this picture, is supposed to be some path in a space. So for every point in M, we just look at the slice. And what we get is just 3 points embedded in R. And as we vary the slice, the points move around. And because of these conditions, the points can also just easily move off the side of the world. And you can also play this sort of game where now you have like R pointing out of the board with the 2-dimensional submanifolds, and here also like they can move off the world and come back in again very easily. So, and the way this is usually topologized classically is like you you consider closed disks and you identify points in the boundary, but not every manifold admits a boundary. And as I said, like as soon as you want to do this, doing it with topological space is going to be hard. Then, okay, so we've seen how it becomes easier maybe to define certain geometrically relevant spaces. What about the second point, that topological spaces is a bad model for homotopy types? So I'll just cite one theorem. This is going to be theorem B. No.
It's not magnetic.
Theorem B, also originally due to Szynski, was a new proof by me. Is that filtered colimits are homotopy colimits in this model, so in set value Sheaves and manifolds. And now, all that you need to do, so with this new model of this configuration space in this sense, you can just show that this here is the colimit as epsilon goes to 0 of all of these spaces. And these are all homotopy equivalencies because they're all Sn. And they're just taking a homotopy colimit with where all the transition morphisms are weak equivalencies. So this here also has to be equivalent to the homotopy type of all the constituent guys of your diagram. So in this sense, we've made precise Siegel's original idea. All right. Any questions about this? So, right. So now I should prove this this theorem A and this theorem B. And to do this, let me start talking about localizations. So recall for C some infinity category and W some subcategory, that the localization of C by W is a functor. It's a new category, W inverse C, and a functor like this called gamma. Such that for all infinity categories D, so if I have an infinity category D, I can consider the infinity category of functors from C to D, and I can precompose to get functors from W inverse C to D, and then I can precompose. So I can precompose with this gamma, and then in here I can consider those functors which carry morphisms in W to isomorphisms in D, and the subcategory is called W. I'll denote with this W script here. And this is a localization if this functor is an equivalence. But for the sake of this talk, I want to give this a new name. I want to say that C is a model for W inverse C. So why would I give such a strange name to a localization? Well, if I take C to be topological spaces, and then if I localize by the ordinary Greek equivalencies, then when I localize this, I just get a functor from topological spaces down to homotopy types. So this recovers the classical sense in which topological spaces are a model for homotopy types. And to further justify this terminology model, let me just recall for you quickly what a homotopy column is. So with C as before, if I have a small infinity category A, and I have a functor from A to C, so as I said, this C is one of these C's, then I can consider a cocone on this functor. So I've extended this original functor to a cocone, and then this guy here is a homotopy colimit if when I take the composition, so if this guy here is a colimit. So, for example, in topological spaces, if I have the inclusion of Sn minus 1 into 2 copies of the fifth, and I take the push out, this gives me a cocone in here, and if I post-compose, this will be a colimit in infinity category. So this is a homotopy colimit in this sense, right? So by model, I really mean you have some category that you're interested in, and you realize it at the localization of some other category, and then you want to know, well, which constructions in this bigger category descend to constructions in the localization. And this is the secret sense in which I intended this verb model here all along. Okay, so let's give an example. So I'll give a whole class of examples which will be very relevant to us. So I'll start with a very big class of examples, and I'll just get more and more specific. So example number 1, if you have some category E and some subcategory D, then if the subcategory admits left adjoint, then this left adjoint will be a localization in this abstract sense. So here the weak equivalencies are then just defined to be precisely those morphisms which are centric isomorphisms by this left adjoint. And then this, if I map out to any further category, it will satisfy this universal property. Okay, let's get a little more specific than this. So for A, some small infinity category, I can consider pre-sheaves on this category. And then I can consider the constant pre-sheaf functor. And this admits both the left and right adjoint. So we have colimits and we have limits like this. So this works just as for ordinary categories. If this is sets or something, this is colimits and limits. And I'm immediately going to erase these two functors, but you have to remember them because they'll come back to haunt us in a bit. So I'll erase these. Now, whenever you have any functor and you have an object in the domain, if you slice over this object in the domain, you get an induced functor to the target sliced over the evaluation of this functor over this guy. So I'll just do something stupid. I'll just slice over 1. So 1 is the final object in this category. This is just the constant pre-sheaf in the 1-point homotopy type. Then I can slice, and then I get the colimit of 1 here. But this here is just nothing else than the classifying space of this infinity category. And since I've already said a bunch of stuff about localizations, I could also just characterize it as the thing that you get if you just invert all the arrows in A. So it's an infinity group point and therefore a homotopy type. And now this left adjoint again has a right adjoint. And it's fully faithful. I guess this is due to Laurie. So this function is fully faithful. So this tells us that homotopy types of the classifying space of A is given as the localization by this colimit functor. So this pre-sheaf category is, in the sense before, a model for this slice category. Okay, and now we finally get back to sheaf and manifolds. So we have our differentiable sheaves, and now we're considering all of them, not just the set valued ones. Okay. So now is when I want you to remember our original triple adjunction that we had here. So this limit functor, if A has a final object, then this limit functor is just given by evaluation at the final object. And here also we can write down a functor which is given by evaluation at the final object. It's called pi lower star. So this is just diff evaluated the final object, and this always admits a left adjoint called pi upper star. And in analogy to this situation, this is like a constant pre-sheaf or a constant sheaf functor. Okay. And if these sheaves and manifolds are supposed to offer us some model of homotopy types, we should have some functor from this guy to homotopy types. And this one is no good, it turns out, for this. So so let us think back to our algebraic topology class. Then we learned that if you have some nice connected pointed space, that the category of covering spaces on your nice topological space is going to be equivalent to the category of sets with an action of the fundamental group. And Kortendijk in the late 1950s, he took this idea very seriously when trying to figure out what a fundamental group is of a scheme. He said, well, if you have a scheme, you just look at all the covering spaces of the scheme, and then you try to extract some sort of group which parameterizes the covering spaces on the scheme. And then now going back to algebraic topology, you can remove the base point from this story. So now you have a not necessarily connected topological space, and then covering spaces on this topological space are going to be the same as functors out of the fundamental groupoid of your group. And this story can also be ported to algebraic geometry, and it turns out that to any scheme you can associate what is called its Étale homotopy type, which is some sort of pro-homotopy type. And in full generality, whenever you have any topos like this functor here admits a sort of a formal left adjoint to pro-homotopy types like this. Now, you don't need to know what this is because we'll go away again really soon. All you need to know is that this functor here commutes with colimits. And then what you can show, or what I show in the article on which this is based, again using like this purely Galois theoretic argument, so just thinking about covering spaces, you can show that pi lower shriek of RD is contractible for all D. So for all RD, if I evaluate it here, I already landed in here. But it turns out that this category can be written as not just sheaves of manifolds, but just sheaves on Cartesian spaces. But basically, because any manifold can be covered by Cartesian spaces. So Cartesian spaces are these guys. Which means that every object in here is generated under colimits by Cartesian spaces, which means that this adjoint here, this pi lower shriek, in fact, factors through homotopy types. So now we get this extra left adjoint, and now we're in a very similar situation to here, where we had sort of three adjoints, and we're interested in the leftmost one. So that this functor here exists was first sketched by Duggar in his 2000 paper on universal homotopy theories for topological manifolds, and I'm pretty sure that the first rigorous proof of this was given by Urs. Urs, maybe you gave the first rigorous proof that this extra left adjoint exists, no?
Yeah, I only know of Duggar's note previously, which
Was
he does odd at this point, right? It's not really complete.
yeah, exactly. Okay, good. So I mean that's what I've been telling people. So now I know that I didn't lie.
That's all I know, nobody ever complains.
Okay, but my method of proof is completely new, because as far as I know, every single other proof requires like either the Nerf theorem or its generalization, the hypercovering theorem by Duggar and Isaacson's, or some variant of this. And these are not trivial theorems, and I'm actually able to recover this hypercovering theorem from this in a very easy way, but I won't get into this today. Just wanted to mention it. Okay, so we have our extra left adjoint. So let's get back to the business of proving theorem A. So now I get to draw a big diagram, which may not be as impressive as David's big diagram, but I'll just have to. I'll take what I can. I'll take what I can get. So let's draw. Okay, let's see. Let's draw diff over here, and us over here. So pi lower shriek was supposed to be the analog of this guy. So we have pi lower shriek like this, and then here we have p sheaves on cart. So cart are just the spaces RD, together with a smooth match between them. And as I said before, diff are sheaves on cart. So we get an inclusion like this. And here we take colimits. So now we'll prove a first simple theorem. So I'll call this guy here A upper star, A lower star, and A upper star. And from this fact here, so if you take the colimit of any representable object, this will be 1. So we have that colimit of RD is 1. So here this is RD over here.
What's that?
Cart infinity is Cartesian spaces, so RD for all D, and then smooth match between them. And there's so if you go around like this, if you go straight down, there's a comparison morphism between these two functors, and because they're both colimit preserving, we learn that what is it that we learn? We learn that pi lower shriek composed with A upper star is equals to taking the colimit, just by extending by our colimits. But then observe that if I take A lower star and I post compose with A upper star, this is the identity. So if I plug an A lower star here and A lower star here, this becomes the identity. And therefore, I get that pi lower shriek is given by colimit A lower star. And this is great because now we've just learned that both of these triangles commute. So if you want to calculate the shape of any sheaf of manifolds, you can just view it as a pre-sheaf on CART and take its colimit. So let's try to go further. So I can write down this functor from delta to CART. Which takes n to the extended simplex. So this is just x0 all the way until xn, such that these guys sum to 1. So if you furthermore impose that these are all between 0 and 1, this is your standard simplex. So I'm taking this away, so this is the hyperplane in Rn. And because of a function like this, I get an induced adjunction. So I have pre-sheaves on simplices, and I can Right, so this bottom one here is just post-composition by this functor. And this here is the left Kahn extension. And for this left Kahn extension, you can just play the same game as you did before to show that this here commutes. Like every representable guy gets sent to a represent. So, but by abstract nonsense, the left guy commutes, but here you can actually just check it using the same method as before, because this here is abstractly isomorphic to Rn. So you just send a representable guy to a representable guy, which in both cases gets sent to 1, and then you can extend by colimits. But you don't need this to get this commutativity. In the other direction, you have that this functor here is cofinal, also known as initial, also known as left cofinal. There are just so many words for this, and they all contradict each other. But all it means is if I take a pre-sheaf on here and pre-compose by this guy, taking the colimit of this original pre-sheaf is the same as taking the colimit of this guy. But that just means that this other triangle also commutes. So all the triangles you have in here commute. And this tells us that any homotopy type that you obtain from a guy in here via the abstract shape functor is just the same as taking its smooth nerve, as in classical homotopy theory. So I'll make this a little bit more precise. So what I mean when I say that that this is just like in classical homotopy theory. So in here, I have the set value sheaves, and any right adjoint restricts to 0 truncated objects, like this. So this right adjoint here restricts to 0 truncated objects, and now now you see if I just take a manifold and I do this whole composition, then that's just taking the total singular nerve with respect to extended simplices. And when you model homotopy types by simplicial sets, the following happens. So we know from our very we know from this very general theorem about reflexive subcategories being localizations, that these 3 functors are localizations. Why? Because I should have said this before. Like these all admit right adjoints, and they're all fully faithful. So these are all localizations. So we know that homotopy types are a localization of homotopy type value p-sheaves on delta. But then something from the point of view of homotopy theory, so if you sort of imagine that you've sort of if you imagine that the only thing you know is homotopy theory, then you'd be very surprised to learn that you can also get all homotopy type bundles considering set value sheaves on delta. And this here just recovers the classical way in which simplicial sets model homotopy types. You just view a simplicial set as a homotopy type value sheaf, and just take the colimit inside of homotopy types. Okay. Now, normally, so this functor here by abstract nonsense admits a left adjoint. And normally it would not be the restriction of this left adjoint, but in this particular case it is by a theorem of Szyczynski, where he just studies the combinatorics of simplicial sets. So this adjunction is just the restriction of this guy. And now we apply the following principle. So let's say that you have, let's say that you have two infinity categories, C and D, and they both have a subset of weak equivalencies. And you consider an adjunction between the two. So this adjunction is between C and D, such that f of V sits inside W, and such that G of W sits inside of V. Then you get induced functors. So when you take the localizations, you get induced functors. So this part here also just makes perfect sense for ordinary categories, by the way. You get induced functors like this. And then you can just show that this here is also an adjunction. And then it turns out, the fact, that this adjunction here is an equivalence. So it's an adjoint equivalence if and only if the unit and co-unit of this above adjunction is a weak equivalency. So by this, I just mean that they're object-wise weak equivalencies. So when you plug in an object C, you go back and forth, you get the co-unit, and you want this to be a weak equivalence. And now let's apply this to the situation. So if I look at the bottom adjunction, then this here just turns into two copies of S, and this is an equivalence. So I learn that the unit and co-unit are object-wise equivalencies. And because this adjunction is a restriction of this adjunction, the unit and co-units are object-wise weak equivalencies up here also. So here the weak equivalencies are just the shape equivalencies. But then I know that this here is a model for S. So now I can use this theorem in the other direction to conclude that this here was also a localization. So we just proved theorem A. So theorem A was that this category is a model for homotopy types.
This is Szyczynski's proof, or your? Or
This is my proof. Szyczynski's proof is very different. But yeah. Yes?
Can you prove that there's some kind of equivalence between the top two guys, or?
Yeah. This is what this showed. This shows that.
Okay, so this is the equivalence, and then.
Right. So I have. So I know that this induces an equivalence on. So when I apply this theorem to this guy, I got an equivalence at the bottom. So then I know that the units and co-units were object-wise weak equivalencies, and because this here is the restriction of this, I know that here the units and co-units are object-wise weak equivalencies, and because I know that S is a localization of this guy, I can now use the theorem in the other direction to conclude that the induced adjunction was an equivalence, and therefore that this functor is a localization. Anyways, so this gives us theorem A. And for theorem B, so recall that theorem B was that homotopy colimits, sorry, that filtered colimits in here are homotopy colimits. So let's first do homotopy colimits in here. Well, so what was a homotopy colimit? Homotopy colimit was a co-cone such that when I map it down, it becomes a colimit. But this here is a left adjoint, which means if I take any colimit in here, this is a homotopy colimit, because I like in a stupid way, right? So all I need to show is that this guy here preserves filtered colimits. And this is true for any topos. So for any topos, the inclusion of zero truncated objects into all infinity topos, the inclusion of all zero truncated objects into all objects preserves filtered colimits. So if I have a filtered colimit in here, filtered colimit in here, and I apply a left adjoint, it's a filtered colimit in here. So this here gives us theorem B. The theorem B was that all filtered colimits are colimits, homotopy colimits. So, so in some sense, if you just take Galois theory very seriously, then everything else just follows very formally and easily. So, okay, this is nice. I've covered a bunch of things which were already known in a nice way. Can I do something new? And the answer is yes. So what is this new thing? So let's go back to topological spaces quickly. So consider the category of topological spaces, and then we have this localization functor down to homotopy types. Then we know that for some CW complex, if I take
So
the
Adrian, maybe this is fading a little bit.
yeah, do I have
There's no other black.
I don't think there's another black, but if there we go.
Blue might work.
Yeah, I'll just use blue then. So topological spaces. So this is just the set of all continuous maps for this open, compact open topology. Then we know that this here is like this is like a model for this guy here, a model for the homotopy type of maps for the homotopy type associated to A to the homotopy type associated to X. And what does this mean? Precisely, this just means that if I take the homotopy type associated to the space, then this is the same thing. Okay, so now let A and X be sheaves and manifolds. You can consider the following. So whenever you have internal hum, you have this evaluation map. To X. And now let us look at the shape functor for a second. So Clough has finite products, which means that it's category accepted, which means that if I take this column, it will preserve products. So if I write the pi lower shriek as A lower star followed by this guy, I have a function which preserves all limits and one which preserves finite products. So I know that this guy here preserves finite products. So if I slap my pi lower shriek over all of these guys, I get a function like this. And then I can just unwind it to get a comparison morphism like this. So we know from topology that it's very useful that this space here is a model for this space. And so similarly, in this sort of differential topology setting, it's very useful to know that this guy here is a model for this space. And this property was christened by Urs and Hisham. So A is said to satisfies the smooth Oka principle if this comparison morphism is an ISO for all X. So this is very similar to this topological setting. If A is, you only need A to be nice for the comparison morphism in the topological setting to be an isomorphism. Oh, and here I should write is an ISO for all X. And Dan Berwick Evans and David de Brito and Pavlov, they have a theorem which says that if A is a paracompact Hausdorff manifold, then A satisfies the smooth Oka principle. And what I prove in my article is that if A is a manifold modeled, so now in the differential geometric sense, modeled on either a Hilbert space or a nuclear Cauchy space or on a nuclear Silva space. So these are all infinite dimensional types of manifolds. Then A also satisfies the smooth Oka principle. And so how much time do I have?
You have about 10 minutes.
Oh, wow, okay.
8 minutes. Either way, we're flexible.
Right. So I'll spend the last remaining minutes trying to explain how one might prove this. And the idea is the following. So the idea of the proof is
So this principle was introduced by Hisham, right? The statement, something like that. And these people just showed it.
so I think this preprint was out before the naming, and then you gave it a name. Is that right? You shouldn't be asking me. You should be asking.
No, we gave it a name. Yeah, definitely.
But
So, I mean, one should say this: the Clough principle in holomorphic complex analysis
Already exists.
That exists. It says essentially that thing for holomorphic manifold. That's from the 60s, I think. Clough. It's really somehow it came to be called the Oka principle. I guess the original author was Clough, but it's known as the Oka principle in holomorphic analysis. Since this is an analogous statement in the smooth world, we call it the smooth Oka principle. I think it's a pretty descriptive name.
well, I mean, I first just called it formally cofibrant, which is like even which is definitely not telling you anything. So I think smooth Oka principle is good.
I mean, it connects it to geometry a little bit, which is
Yeah.
the whole point from our perspective.
No, I mean, the term appeared long before our preprint. We discussed. I mean, Pavlos, they've been theorems from 2014.
Oh, okay.
So we've been discussing this for a long time.
Who's speaking? The speaking in the paper 2000.
The smooth version is first claimed with maybe I don't know, maybe a less elegant proof, but it's first claimed improvement by Dmitry Pavlov in 2014 in unpublished preprint, unpublished note, right on this website, but widely circulated.
You call it formally cofibrant.
Yeah, I call it formally cofibrant originally.
They call it modial cofibrant.
Oh yeah, right. Yeah, so in my current article, it's called satisfies the smooth Oka principle, or because that's a bit of a, I mean, it's hard to integrate into some sentences, so I also call it this Oka cofibrant, which I think splits the difference.
By the way, did you think about if you can actually use your technology to prove the original Fokker principle?
So,
Outside of maybe Stein manifolds?
Stein manifolds aren't. I don't know. I don't think I can. So what I can definitely prove is that like sheaves on complex manifolds or something that these that this is going to be a cohesive topos. That is basically just because you have. Yeah. I mean, it's definitely locally infinity connected.
Oh, but probably not strongly.
You don't think it preserves finite product?
I think it is locally, right? Don't you have to have, you have all these patches that are not contractible.
I mean, any complex manifold can just be covered by hyperdisks, and they are contractible now. Polydisk, sorry. So I was already thinking about hyper sheaf.
The statement that this thing is cohesive, this is without that word in Quick Hopkins' article on Hodgson cohesion. They actually prove that.
Oh, okay. So it's not a new
They
statement.
don't use the terminology.
Right. But like any sort of thing that's just built from locally contractible pieces is this is going to be like, you know, maybe not necessarily cohesive because you don't know if the extra left adjoint preserves finite products and so on, but no, if you know that the locally contractible guys are closed under finite products, then you will also preserve finite products by the same.
You may not have that survival
Right.
Condensed setup, that's the thing.
No, in the condensed setup, you also don't have the extra left adjoint, I don't think.
Well, I thought in some points you do actually.
Oh.
But wasn't that the falsest claim that actually you do right, you do have the left one?
In the condensed one, you don't have the left adjoint, but you also don't have the extra. You don't have the extra left one, but you also don't have the extra right one. But that's precisely what she reasons. So
Okay.
condensed things don't form topos. So if you work relative to a graph in the universe, then you do have the extra right one. That's not it.
Right. But this also makes moral sense because like the cohesive homotopy types are sort of a thing that you're trying to be cohesive over. So after this digression, the idea of proof is the following. So let's say that you have objects S, D, and X, which all satisfy the smooth anchor principle, and consider the following push out. Push out like this, and I've chosen very deliberate notation. You should think of this here as attaching some sort of cell to X, but like just formally, it's just a push out. Then if then we have that this new guy satisfies this Miloka principle if and only if. So I can put all of these guys. So I'm sorry, I'm just gonna exchange my X with an A so that I don't get confused later on. So what I want to map this guy here into some object X. So let's do this for all guys. And this turns all the arrows around. Then this guy here satisfies the Smudoka principle if and only if this the square here is a pullback. And why is this? Well, I get a natural transformation. Sorry, if this is a homotopy pullback. This is definitely a pullback. This is always a pullback. but you want this to be a homotopy pullback. So you want that if I apply pi lower Schwick to this, that this is going to still be a pullback in homotopy types. So let's hope that the black has recovered by now. So let's put a pi lower Schwick everywhere. Then, so this guy here turns into pi lower Schwick S to pi lower Schwick X. And then this guy here turns into pi lower Schwick A to pi lower Schwick X, and so on. And this here is definitely a pullback. This here's and then you have a comparison morphism, which goes in this direction, which by assumption, this here is a weak equivalence, this here is a weak equivalence, this here is a weak equivalence. And because we know that this here is a pullback, this is a weak equivalence if and only if this thing here is a pullback, which is precisely saying that this original square was a homotopy pullback. So what the question of proving the smooth Oka principle boils down to, it just boils down to showing that pi lower Schwick, that it preserves certain pullbacks. And right, so we've already seen that pi lower Schwick, it preserves a bunch of colimits. I mean, it preserves all colimits because it's just a local, it's just like a reflection, but it doesn't preserve many limits. Now, if we just go back to our very original example of a model like this. So what can we do in order to find homotopy limits and homotopy colimits? Well, we put a model structure on topological spaces, and then we know that if a bunch of objects are fibrant and a bunch of the transition morphisms are vibrations and so on, and we take the colimit, this will be a homotopy limit. But the definition of a model structure compiles with zero problem on infinity categories, and also all the theorems about which limits get taken to limits in the localization, they all still hold. So model structures are really about localization, not rather than being some sort of alternative to infinity categories or anything like that. So what you do is you just slap, you construct certain model structures on these sheaves and manifolds, and then you find a sufficient supply. You find a sufficient supply of morphisms S to D, such that these restriction morphisms are vibrant. Right. So you want sufficiently many morphisms like this, so that when you pull back along them, after mapping into X, that these are vibrations. And this is what I do. And then I have a bunch of cell attachments, and then I can just show that any of these infinite dimensional manifolds are homotopy equivalent to some sort of cell complex that you can build from these guys, and being satisfying the smooth Oka principle is equivalent under R homotopy equivalence, and then you're done. So that's the end of my talk, and I thank you for your attention.
Any further questions for Adrian? I think we had quite a bit of discussion, but any other questions left?
Let's see, do I use observe that you can just do continuous status instead of valutative constraint? It's kind of a key step for maybe something simpler.
Yeah, I'm pretty sure it does, right? So you know about Szynski's secret site thesis.
No, I don't know.
So Szynski has his thesis on test categories, and then has like this site thesis on test toposes. and this is on his website. And so yeah, and there it's in chapter 5, he proves this theorem that I started off with, and there he sort of very generally says, well, if you have some not necessarily full subcategory of topological spaces, which can expand by objects which can be covered by by contractible guys, then this will give you a model for homotopy types.
How's this thing called?
It has it's in French. It has faisceau in the title somewhere.
And topos?
I don't think it has topos in the title. It's really just le faisceau comme modèle de type homotopy or something like that.
But that's his main thing.
It's been, oh, that's a preface. Look, yeah, that's the one.
Good. Any other questions? Okay, if not, let's thank Adrian again for the very nice talk. Thank you, Adrian.
Yeah, that's sort of one remark on the discussion of the condensed set.